In this video, I'm going to solve this question. The recommended daily dietary allowance for zinc among males older than 50 years is 15 milligram per day. This article reports the following summary data on intake for a sample of males aged 65 to 74 years. So we are given that the sample size, that is n, is equal to 115. The sample mean is 11.3 and the sample standard deviation is 6.43. Does this data indicate that average daily zinc intake in the population of all males ages 65 to 74 falls below the recommended allowance? So now, first of all, let's say that mu is the true average daily zinc intake. So mu is the true average daily zinc intake. So this is a population parameter actually. Now let us define our null hypothesis and alternate hypothesis. We are asked that we have to test that average daily zinc intake in the population falls below the recommended allowance or not. So that means we have to test that mu is less than 15 or not, because the recommended allowance is 15 mg per day. So this is one claim. The counter claim is mu greater than equal to 15. So these are the two claims that we have. Now because this claim has equal to sign, so this is our null hypothesis and this is our alternate hypothesis. Now let us see what all information is given in the question. So we are given that our sample size is large, n is equal to 115. The sample mean, which I am denoting by x bar, is equal to 11.3 and the sample standard deviation, which I am denoting by s, is equal to 6.43. So this is the information that is given to us in the question. Also note that we have a less than sign in the alternate hypothesis. So this means that this is a left tail test. So this is a case of left tailed test. Now we have to decide which test statistic to use to test this hypothesis. So see, we are not given anything about the population. We don't know whether the population is normally distributed or not. But because our sample size is large, our n is equal to 115, so we can use central limit theorem, and using central limit theorem we can say that x bar will be normally distributed. So irrespective of how the population of x is distributed, x bar will be normally distributed, and this follows from central limit theorem. Now because x bar is normally distributed, we have to decide between whether to use t-test or z-test. Now note that the population standard deviation is not given. So the population standard deviation, which we can denote by sigma, is unknown. What we have is sample standard deviation, which is equal to 6.43. Well, in this case, even though we have no information about the population standard deviation and what we know is sample standard deviation, we can still use z-test. And this is because our sample size is large. And when our sample size is large, the t approaches z only. So that's why we can use the z-test safely. So in this case, the formula to calculate z is equal to, so z calculated is equal to x bar minus mu divided by s divided by under root of n, where mu is the value of the mean under the null hypothesis, which is equal to 15. S is the sample standard deviation. So we can use this formula of z in this case. Now we are given that x bar is equal to 11.3 and mu under the null hypothesis is 15. Sample standard deviation is 6.43 and n is 115. Solving this, we get that the z calculated is equal to minus 6.17. So now we have our z calculated. We just have to compare this z calculated with z critical to decide whether to reject the null hypothesis or not reject the null hypothesis. But there is a twist in this question. In the question, we are not given the value of alpha. So we don't know what is the value of alpha. Consequently, we cannot draw the rejection region and we cannot find the z critical value. So what do we do in this case? Let's see. So let's draw the z distribution. So let's say this is how the Z distribution looks like. And we have calculated that Z calculated is equal to minus 6.17, and we are not given alpha, so we cannot find the Z critical value directly. To say something about this hypothesis, first let's have a look at Z table. As you can see, this is a cumulative probability table. And now let's have a look at some of the Z values. So let's say that Z is equal to minus 2.7. And when Z is equal to minus 2.7, the corresponding probability, or I should say the corresponding cumulative probability, is 0.0035. So this means if Z is equal to minus 2.7 is here, then the probability that any particular Z value will be to the left of this value is 0.0035. So this is 0.0035. Now let's have a look at one more Z value. Now let's say that Z is equal to minus 3.4, and in this case the cumulative probability is 0.0003. So let's say that Z equal to minus 3.4 is here, and the probability that Z will take any value to the left of this value, that is this area, is equal to 0.0003. So this means that the probability that any Z value will lie to the left of minus 3.4 is very less. It's approximately 0. Now let's have a look at the Z value that we calculated. So we calculated that Z is equal to minus 6.17. Well, note that the probability that Z will lie to the left of minus 3.4 is 0.0003. So ideally the probability that any particular value of Z is less than this Z calculated will be approximately 0 only. So it will be 0.000 something. So minus 6.17 will be to the extreme left. Say it is somewhere here. Okay, so say this is minus 6.17. This is minus 6.17. Okay, now though we are not given any particular value of alpha, we can still reject this null hypothesis. Think of it in this way. Let's say that alpha is equal to 1%. And if alpha is equal to 1%, the rejection region will be somewhere to the left because it's a left tail test. And if you find the Z critical value when your alpha equal to 1%, you will see that it is equal to minus 2.33. So say minus 2.33 is somewhere here. And consequently, this is my rejection region. And here alpha is equal to 1%. Well, this area does not look like that it contains only 1% of the Z values, but I hope you're getting the point that I'm trying to make. So even when your alpha is as low as 1%, we are going to reject the null hypothesis because your Z calculated is way too extreme to the left. Even if you take your alpha to be equal to 0.5%, even then you are going to reject this null hypothesis. So the conclusion is that even though we are not given any particular value of alpha, but the Z calculated is way too extreme to the left. So that means irrespective of the value of alpha, we are going to reject this null hypothesis. So the conclusion is that in this case, we reject the null hypothesis. So that means we reject the null hypothesis that mu is greater than or equal to 15. So this means that the true average daily zinc intake is indeed less than 15. And this is all for this question.